Hey guys, welcome back. Today we're going to talk about the inverse normal distribution, which is similar to the normal CDF or cumulative density function. But now we're going to be working backwards, starting out with percentages and finding out what those bounds would be for it. So very similar, very easy day. Hopefully I can get through this pretty quick. So anyway, I got a really cool visual in front of you right now. This is the average American male compared to some other European countries or typical adult males in other countries. So this whole thing actually comes from the United Kingdom. So this is something that was put out by the UK, and you can tell that because where it lists the weight, the average weights, it tells you 14 stone. ST stands for stone. Sounds pretty archaic to me, kind of medieval, I suppose. But they actually do refer to themselves in stones. So 1 stone is 14 pounds. So it's similar to, I mean, it's like pounds, and since we use pounds, no one else does that. Of course, the rest of the world uses kilos. So not really any surprise here. The American coming in weighing as the heavyweight, the favored champion of all the contenders here. What's kind of interesting is that the Nederlanders, so the Netherlands here, with an average height of about 6 feet, they are actually the tallest of the group that we're looking at here. And then Germany not too far behind them, and then the United Kingdom similar, and then even shorter than the Americans are the Australians from down under. Anyway, so couldn't help myself there. But yeah, anyway, there's some interesting information there you can pick up on it. So we're going to be talking about weights here. So let's look at some distributions and heights, of course. So probably more politically correct, we'll talk about heights. So heights of adult women and American men here. So we have this clearly bimodal distribution for women and for men here. Not quite sure where I even got this. This is from the CDC from 2007. So adults aged 18 to 64 or 80. Wow, 86. Sorry about that. So we have two different distributions here. The mean height for women is going to be, let's see, that's going to be 5'3", 0.58 inches with a standard deviation shown there. And for men, it's going to be 5'9" and that many inches with a standard deviation there. So noticing between the two distributions, first thing you might notice is that the women's distribution is going to be, of course, a smaller average height. But what's more interesting is that they have more consistency. So they have a smaller standard deviation. So there's more variation in men's heights than there is in women's heights. So they tend to be shorter. Women tend to be shorter and more consistent. And you can see that in the width of the two normal bell models that we could model both of these from. The women's seems to be taller and narrower, where the men's is shorter and wider. Talking about the bell curve, not their actual heights or weights, because that's not what we're doing. Anyway, so kind of cool. And if we actually overlap these two distributions here, what's interesting is this overlap in the middle would actually probably stack up. It might even make the whole thing look unimodal. But anyway, we're not going to get into that too much. So this is another one I thought you might find interesting. Besides that Dallas Cowboys game, the comeback. Oh wait, sorry, spoilers if you didn't watch that game, but it was really, really good. That onside kick left the Atlanta defense mesmerized, the first time you spun a spinner or a fidget spinner. They're like, what's going on with the ball? And they didn't know what to do. It was amazing. Anyway, so now you should watch the highlights. So this is the NFL combined weight distribution. So of all the NFL and AFL teams, that's the combine put together, of all these players, they listed their weights. But what's interesting is that we're looking at subgroups, just kind of like male and female subgroups. We can see there. We can actually look at subgroups by position. So if you know what those positions mean, I might know half of them. I don't really know a lot about football. But anyway, so if you look at those positions, you can kind of see all of these positions here. Those are going to be your linemen on the offensive and the defensive line, all your 300-pounders. The quarterback, let me see where the quarterbacks are. Those are the purple, so we actually have quite a few, the purple. And so we have some quarterbacks that are lighter, about closer to 100 or about 200 pounds to, looks like we're going to about 250 pounds, which is pretty big. The quarterbacks have to be pretty big or they're going to get injured and won't last very long. So the most common here, our mode, of course, is going to be 210 pounds. So that would be, that's the most common weight for an NFL player. And then down here you have the punter and the kicker, which are going to be the light colors that kind of show up on here on the very top layer here. And if you're wondering what this is right here, this is actually my weight. So this is the reason why I don't play for the NFL, because I would die. But anyway, there are kickers and punters that weigh more than I do in the NFL. So anyway, that's why I do the math and the stats for the NFL players instead of trying to get out there and getting destroyed. I would probably die. So anyway, really cool. If we broke these down by so this light green here, that's going to be the cornerbacks. They've got to be pretty light. They got to keep up with the wide receivers, who are also very light. That's going to be the light blue there. So you can see those two. In fact, it looks like the corners are even slightly smaller than the wide receivers when it comes to weight. Yeah, anyway, so some really cool stuff. You could stare at that for days, but I'm going to move on because you can always pause the video if you want. All right, so American adult height, difference between women and men. So we have two separate distributions, and we're on the assignment already, just jumping right into it with the example one. So the CDC conducted a survey in 2016 of heights of American adults. They found that males had an average height given, with standard deviations given as well. Females had their averages with a standard deviation given there. Alright, with a smaller standard deviation for the females, we pointed out. Label an appropriate model for your sex. So either fill in the one for female or the one for male. I'm not going to fill in either of them, I don't think. No, I do. I fill them in on the next one. So, boom. Ha! You're welcome. But make sure you know how to fill those in, right? So the next thing we want to do is graph your height on the normal model and find the z-score for your height. So I am, let's say, 6'1", somewhere in there, like 6'1.5", but we'll run down 6'1". So if I'm 6'1", that's going to be 72 inches is going to be 6 foot, so 73 inches. So to find my z-score, it's going to be slightly above one standard deviation. But let's go ahead and find my z-score. So if I am 73 inches minus the mean for the male distribution, which would be 67.17 inches, okay, and then we're going to divide that by standard deviation of 3.09. One more thing, if you want to do all this all at once, what I recommend is that you actually hit the alpha X button. Let's try that again. So alpha X, and then you can put it in as a fraction. That'll keep you from making some mistakes, which I've seen. So 69.17, and then in the denominator, 3.09. The other way to do this, of course, would just be to use parentheses, or just do it separately like I did. Alright, so you get the same answer. I am 1.224 standard deviations above the mean. So then the question I have next is, what is the percentile for that? So what percent, so if I'm somewhere about right there, what percent of American men am I taller than? So to find that out, we want to know the area underneath the curve going all the way up to 73 inches with this distribution. So the way we would put that in is through the normal CDF, the cumulative density function. We want to know the area under the curve, and it's a cumulative, so it's going from the left and adding it all up, and it's the density underneath the curve. So cumulative density function, CDF. Kind of like an interval. It really is an integral, not interval, integral. So we're going to do second variables to go to distribution. We're going to do the second option, which is the normal CDF. Our lower bound is going to be basically negative infinity. That's what they're showing there. That's going to be the default. Your calculator will always go back to. The upper bound, we're going to do 73 inches. You, of course, do yours, not mine. For the mean, because we're not doing z-scores, we actually have to fill in this information. So for men, it's going to be 69.17 with a standard deviation of 3.09, and then hit paste, and there you go. So it looks like I am taller than or equal to 89.2% of American males, which is pretty cool. So if yours was below the average height, then that means that your z-score would be a negative z-score, meaning that it would be less than half or less than 50%. So because my z-score was about 1.25, that meant that I was it would be a positive z-score, which would give me a percentage that is higher than the 50 percentile, which is the median, right? Okay, cool stuff. So you can find out your z-score. So yesterday we found out the z-score for your birth weight, which is politically correct because we're not going to do your weights, spoilers, but we can do birth weight because no one cares about that. Also your heights and the ACT score. So kind of fun. You can know kind of where you rank among American male population or female population. All right, American adults for women's height. So we just did an example with the men, so now we'll do the women here. So let's go ahead and find, use your calculator to find the first and third quartile for American female height. So if you just filled in all the values for the male, you can do the male, it's fine. Or you can just follow along with me. So for the first quartile, this is actually, now we're working backwards. Remember, the first quartile is going to be the 25%. So we want to know the area under the curve. Oh man, I really should have made that slide, but I didn't do it. I wonder if I could do it real quick. No, I can't, because it's a different file. Anyway, so basically we want to go up to the 25 percentile, which if I actually kind of graphed it here, you can see that the 25 percentile is going to be, actually it's right there, right? That's the first quartile. So we want to know what is that, the actual weight. So we need to find, we know we're starting out with the area under the curve, and we want to work backwards to find the actual bound for that. So instead of using the CDF, we're going to use the inverse normal. So to find that, we go to second variables and go down to the inverse normal, which is the third option. So yesterday we talked about the second one, and now we're going to do the inverse, so just working backwards. We want to know the area under the curve. Okay, so we want to do a quartile, so we're going to do 0.25, so that's 25%. Make sure you have the decimal in the front, not just 25. And then we're not doing a z-score. If we want to know the z-score, we just do 0 and 1 for the standard normal. But we're going to actually put in the information for women, ready, and the standard deviation of 2.76. Oops, make sure you have a decimal there, 2.76. Okay, and then the tail. So this is asking, do we want to calculate the, are we calculating the area from the left, from the right, or from the center, which is actually pretty cool. The older calculators would do this. We're going to calculate from the left because we're finding the first quartile. Then we're going to hit paste and then hit enter, and that'll tell us that it's going to be 61.71, which I should have here. Yeah, so 61.71 inches, which is 5 foot and about 1.7 inches. So if you are taller than 5'1" or 1.7, then that means you are above the 25 percentile. So you're taller than 25% of American women. So there are 25% of American women, adult American women, of course, that are shorter than you are. And by the way, you guys are not all yet adults yet, so you could still grow. And I did actually grow a few inches when I was in college, so that can happen too. So don't be sad. Okay, so then the third quartile is going to be the other part. Now we could do the exact same thing that we did before. In fact, if I wanted to, I could just arrow up and hit enter, and then for the area, change it from 25 to 25 to 75, and that'll give me the third quartile. But let me show you another way, which is actually pretty cool. So we're going to go second variables, third option, and I'm going to find the inner quartile. So the inner quartile range is the middle 50%. So I'm going to change the area to 50%. The mean and standard deviation same, but now I'm going to calculate from the center. When I do this, looking at the box plot, I'm finding the middle 50% calculated from the very middle, and that's going to actually give me my first quartile and my third quartile all at one time. So whenever I do that, notice it's going to give it out and export it in interval notation. So I'm going from 61.71, does that sound familiar, to the maximum of 65.441, which is exactly what we got for that value. So pretty cool, kind of groovy. I don't know how groovy. I don't know how often you'll actually be asked to find the inner quartile range, because typically when we're using a bell curve, we're using mean and standard deviation, not box plots and IQR. So it's actually really rare to see a box plot on top of a bell curve, but I am going to go a little bit deeper into that just so you can actually see just a little bit about like where we call outliers. So that's part E for your part. So what's the inner quartile range? If we subtract those two, it'll give us 3.73. And notice the IQR is going to be larger than the standard deviation. So when we're comparing, like if you want to know if a distribution is skewed, you can compare the mean to the median. And if the mean is higher than the median, that means the distribution is skewed to the right, right? If the mean is less than the median, that means the distribution is skewed to the left, right? Or the lower values. But when we can't necessarily do the same thing, comparing a standard deviation to an inner quartile range, because the inner quartile range is always going to be larger than the standard deviation when we're dealing with normal, data that's either normally distributed or roughly unimodal and symmetric. Okay, so you can't necessarily compare those two like apples to oranges. They're just different. Okay, so the next question we have is if we calculate the z-score for the right fence. So I've got my box plot here. I want to do 1.5 times the inner quartile range, then add it to the third quartile. Okay, with z-scores, and that's going to give me the right fence. I want to calculate the z-score for the right fence to figure out where it is here. And you can kind of see where it is on there, but this is actually going to be pretty fun. So what I'm going to do is I'm going to go into I'm going to do second variables, inverse normal. I'm going to calculate the middle 50%, but this time I'm going to use z-score, so I'm going to center it at 0 with standard deviation of 1, and then hit paste, and that's going to give me my two, my left and my right z-score for the first quartile and the third quartile, which is going to be about 0.674. So to find the interquartile range, I'm actually going to subtract those two, or just double one of the sides because it's the exact same thing. So 0.6745, we'll just do that. I'm going to multiply it times 2 because this 0.674, that's going to be this half, okay, going to one side for the third quartile. And if I double it, that's going to give me the entire interquartile range. The same thing if I would have subtracted it, but you're subtracting a negative, so it's going to be adding the two together. So no big deal. And that's going to be the interquartile range. Now I'm going to multiply it by 1.5, and then I need, oh, well, yeah, that's pretty much it. Let me double check. Yeah, so that's interquartile range times 1.5. Oh, no, I actually did that wrong. Okay, so now the last step I need to do is add that to the third quartile, which we said was 0.68, or sorry, 0.6745. Okay, which is going to be about 2.7. So whenever we were dealing with median and interquartile range, we would have a standard deviation. We would consider an outlier if it was beyond 2.7 standard deviations. And for a bell curve, we would consider something to be unusual if it's more than 2 standard deviations. So this actually should be further out. So that's about 2.7. So it should be about right there. And for us, we would consider something an outlier if it was beyond 3 standard deviations. We would consider it unusual if it was beyond 2 standard deviations. So anyway, kind of cool. Just trying to cross the difference so you can see the difference between when we're dealing with median and interquartile range and mean and standard deviation. So that value is actually going to be wrong. Okay, so that's it. Let's look at number 40. IQs revisited based on the normal model of centered at 100 and standard deviation of 16. Describe the IQ scores. What percent of people's IQs would you expect to be over 80? So they give us the model. It's going to be centered at 100, standard deviation of 16. This is graphically what that would look like. We want to find what percent are over 80. So when we're doing this, we're going to 80, but it's going to be over 80, so that's going to be something that looks like this. So we want to find the area under the curve there. So if we're finding the area under the curve, we're using the CDF, so second variable CDF. Our left bound this time is actually going to be 80. Our upper bound, we'll just do 999. We're not using z-scores, we're using the actual statistics here. So the actual parts from the distribution. So the center in this case is going to be 100 and the standard deviation is 16. Then hit paste. Alright, so it looks like that's going to be 89.4%. Okay, so 89.4. What about under 90? So under 90, now we're going from the other direction. So all the way up to 90, which can be somewhere about right there. Alright, so again we're finding the area under the curve, so second variables, normal CDF. Our lower bound this time is going to be negative 999, so we have to use that negative symbol, 999. The upper bound we're going to go up to 90, still centered and standard deviation is the same, which is going to be 26.6%. Okay, no big deal. And the last one is going to be between 112 and 132. So between 112 and 132. Well, this is actually going to be kind of backwards, but you can get the idea. So we want to find the area, the wide area in between the two. So I didn't set this one up right, but it's okay. So same thing, second variables and normal CDF. Our lower bound, they're going to tell us is 112, and our upper bound is 132. And still centered at the same thing, and that will give us our area, which is going to be 20.4 if we round. Yeah, so 20.4%. Okay, 32. More IQs. So now we're going to be working backwards. They're going to give us a percentage, and we want to find what the limits or the bounds for those are. So what cutoff value or bounds or whatever. Okay, so what's the highest 5%? So the highest 5% is going to be something like this. I guess I should probably lock that in place, which means this one's probably not locked in place either. Sure enough, what do you know? All right, so we want to find the highest 5%, so that's actually going to be beyond that. You already know that. So we're working backwards, so second variables, we're going to do the inverse normal. The area we're going to do is 0.05, don't just do 5, it's got to be a decimal. We're not doing z-scores, so we're going to use the actual data, or statistics, in 16, and we're measuring it from the right, which is actually really nice. If we had an older calculator, we'd have to do an area of 95%, and it defaults to measuring everything from the left. So the newer calculators are really nice. They got some new functions in them. So that's going to be 126. So you'd be in the top 5 percentile if you had an IQ score of 126.3 or above. Alright, lowest 30%, so same idea, except now we're looking for the lowest 30%, which is going to be something along the lines, I think it's actually going to go into there a little bit. So we'll do the same thing, second variables inverse normal, so third option. The area we want is 30%, and we're measuring it from the left. Alright, so 91, pretty well what I said, or was estimating, 91.6, middle 80%. So it's kind of like a interquartile range, but instead of 50% from the middle, we want to measure 80% from the middle. So graphically, that would look something along the lines of this. I know, that is so cool. And somewhere over there, so that would be about 80% measured from the middle. And of course, we can do the same thing with the inverse normal. So second variables, third option, inverse normal. We're going to do 80% for our area, and we're just going to change it, of course, to measuring from the center. And that's going to give us our bounds from the left to the right. So that's going to be anywhere from 79.5 to 120.5. So if you have an IQ score of 79.5 to 120.5, then you're in the middle 80%, the middle 80 percentile, or the middle 80% of all IQ scores. I think that's it. Yeah, that's it. Only 20 minutes, 22 minutes, or whatever. So pretty short. I hope you guys enjoyed that. It's really simple compared to what we did yesterday. There is another even problem, I think, on the homework, which I didn't set up because it's really, really, really late. Body temperature is 48, and then you should know how to do example 3. But if you guys don't know how to do it, join me for the tutoring, and I can help you guys out. Besides that, have a good day.